Your instructor sneaks into a dark MBTA tunnel at night to spray a letter L on a train as it goes by. The train is moving right to left at 5 meters per second. The instructor can't see the train, so he draws the letter L as if the train is at rest. He sprays a vertical line 1 meter long and then a horizontal line 1 meter long, with his hand moving at a constant speed of 2 meters per second. What mark does he leave on the train? The main concepts involved in this problem are relative velocity and vectors. To get an intuition for what the mark on the train will look like, I'm going to move the sheet of paper from right to left while drawing an L. After simulating the scenario, we see that the mark left on the train should be an elongated L shaped, like this here. We are told in the problem statement that the train is moving from right to left at a velocity of 5 meters per second with respect to a stationary origin. This means that if an observer was standing on the side of the platform, he would see the train moving at 5 meters per second. Mathematically, we write this as the velocity of the train with respect to this origin is equal to negative 5 meters per second in the x direction and 0 meters per second in the y direction. We are also told that the instructor makes two displacements of length 1 meter, moving his arm always at a constant velocity of 2 meters per second. This again is with respect to a stationary origin. The first displacement is vertical. That's when the instructor takes the can and makes this downward movement. In this case, we write his movement mathematically as the displacement of the instructor with respect to the origin is equal to 0 meters in the x direction and negative 1 meters in the y direction. Similarly, his velocity of the instructor with respect to the origin is 0 meters per second in the x direction and negative 2 meters per second in the y direction because the can is moving down. The second displacement was horizontal when the instructor makes this horizontal portion of the letter L. In this case, the displacement of the instructor's arm with respect to the origin is 1 meter in the x direction and 0 meters in the y direction, and this happens at a velocity of 2 meters per second in the x direction and 0 meters per second in the y direction. All of these velocities and displacements are given in the reference frame of the origin. In order to answer this question, we need to solve for the two displacements, the vertical and the horizontal pieces, made by the instructor with respect to the train. That is, what is the displacement of the instructor's arm with respect to the train during the downward portion, and what is the displacement of the instructor's arm with respect to the train during the horizontal portion of the movement. In order to solve for the displacements of the instructor's arm with respect to the train, we're going to need a velocity and a time. The velocity we need is the velocity of the instructor's arm with respect to the train. The time we need is the amount of time necessary for the instructor to make each mark. In the reference frame of the origin, we are told that the instructor makes a displacement of 1 meter and moves his arm at a velocity of 2 meters per second. The amount of time it takes for this motion to be completed is the division of these two numbers, which results in a half second. The time it takes the instructor to make this movement is invariant. That means that it's the same across all reference frames. So, even in the reference frame of the train, it will still take the instructor 1/2 second to make the vertical portion of the L and 1/2 second to make the horizontal portion of the L. In order to find the velocity of the instructor's arm with respect to the train, we use the subscript squeeze formula. That is, the velocity of the instructor's arm with respect to the train is equal to the velocity of the instructor's arm with respect to the origin plus the velocity of the origin with respect to the train. The velocity of the train that we're given in the problem statement is the velocity of the train with respect to the origin. In order to rewrite this velocity of the origin with respect to the train, we reorder these two subscripts and create a minus sign. Then we can now find the velocity of the instructor with respect to the train is equal to the velocity of the instructor's arm with respect to the origin minus the velocity of the train with respect to the origin. At this point, we have all the necessary information to find the vertical and horizontal displacements in the reference frame of the train. Let's look at the vertical displacement first. The vertical displacement of the instructor's arm with respect to the train is equal to the velocity of the instructor's arm with respect to the train during the downward motion times the amount of time it takes to complete the movement. We substitute in this formula here for the velocity of the instructor's arm with respect to the train, plug in the information we got from the problem statement, and complete the multiplication to find that this, what was originally a downward movement in the instructor with respect to the origin reference frame, is now going to be this angled vector where it goes 2.5 meters to the right and -1 meters down. The exact same procedure is used to find the horizontal displacement. This time, we substitute in the values that correspond to when the instructor moved his arm in the horizontal portion of the letter L. We do this and find that this horizontal component has been elongated. So now the mark is 3.5 meters long instead of 1 meter long. To finish the problem, we graph these two displacements here. When we do this, we see that we still have a shape that is similar to the letter L, but this vertical portion has now become slanted, and the horizontal component is much longer. If we were to compare this shape to the shape we made at the beginning of the video, we see that they are roughly the same,